All right. So guys, today we're going to have exercise 3B, increasing and decreasing functions. So we're page 30 of your notebook. We will have time towards the end of the lesson to go over that conjecture problem that some of us, we didn't finish cracking at the end of last lesson. So that'll happen today, but we're dedicating most of the lesson to exercise 3B. So what we're doing here is we're talking about when is a graph, when are you increasing and when are you decreasing. So you learn about this in year 11 when you start to talk about it. If it's increasing, we're always talking about moving from left to right. And it's going to be increasing if you're moving up, if you're walking up a hill, and it's going to be decreasing if you're walking down the hill. So what we can see, this is the first function we're presented with. It's a quadratic, and you can see if you were to walk along this graph, you're going to be decreasing until you get to positive 2, x is positive 2, and then you're going to be increasing, okay, for values larger than 2. You're going to be walking upwards. So you can see this from the graph, but we're going to use calculus methods to tell us when it's increasing and decreasing. So there's going to be a little bit of a process here. The link we're making, if you're reading the text that's presented above, is the slope function, all right? That's the first derivative. The slope function tells you when the slope is positive and negative. And what you notice is if it's decreasing, you've got negative slope. You're walking downhill, okay? So when the slope function is negative, decreasing. When the slope function is positive, increasing. That's the link that we're making today. So the process is always the same. We're going to start with the function and we're going to differentiate it. We need the derivative function. So when we differentiate this quadratic, we're going to get 2x take 4. And then we're going to draw the sign diagram of the derivative function. So I'm going to draw this sign diagram manually for you. All right? I'm going to talk about how we draw the sign diagram manually. The first thing we need to do is find the roots. All right? We need to find when does the derivative function equal 0. One of the values that make the derivative function equal 0. Where does it cross the x-axis? And we go through and solve this. All right, we've got x is 2 is the root. All right, so we're going to draw a sign diagram. We're going to have a root at 2. And then we want to determine when is it negative and when is it positive. When is it negative, when is it positive? Now there is a way that we can look at this type of function and know intuitively, but I'm going to make a mathematical argument for you here. All right, we want to know when is it negative, when is it positive. So we're going to choose any number to the left of positive 2. Think of that's an x-axis. Any number to the left of positive 2, could be 1, could be 0, could be minus 1, could be minus 2. It doesn't matter. Any number is going to give us the same result. So let's choose when x is 0. When x is 0, what does the dy on dx function evaluate to? If I put the number 0 in here, I'm going to have 2 times, I'm going to write it out, 2 times 0, take away 4, I've got minus 4. The magnitude, the size of it's not relevant. The important part is that it's negative. To the left of this root, it is negative. Okay, so that's going to be a negative there. And we can make the same argument for numbers larger, boys. We can make the same argument for numbers larger than 2. So we'll say when x is positive 3, could be positive 4, could be positive 5. What's dy on dx? It's going to be 2 times 3. Take away 4, 6, take 4, it's positive 2. Okay, the number's not significant, but the fact that it's positive. That means in this region, for all values larger than 2, because this evaluated to a positive, we're positive in this region. So that's how we draw a sign diagram, right? That's how you do it manually, okay? Nonetheless, you can get this information from your graph. So I'm going to show you a few calculator hacks in a moment how we can arrive at that. So what this tells us, this is very important. Let's label it as well. This is the sign diagram of dy and dx. And this is important because it tells us the original function has negative slope until you get to 2. Remember, this is the sign diagram of the slope function, right? We have negative slope until you get to 2, decreasing until you get to 2, and then we have positive slope for values larger than 2, increasing after that. So that's what we're doing here. That's the calculus method, right? You differentiate it, you draw the sign diagram of the derivative, and then you answer. Increasing, but x is, we always include the point, greater than or equal to 2. Decreasing, x is less than or equal to 2. Okay, so you can see we're decreasing until we get to the point 2, slope is 0, and then we're increasing. Now, I said before, I've made a manual argument here. There's like 3 ways we can do it, right? We can make this manual argument, it takes a lot of time, okay? We can know from looking at this that it's going to have this, negative, positive, because this is the equation of a line. It has a positive slope. The slope of the line is positive, which means we look like that on the Cartesian plane. Okay, which means it's coming from below to above. It's going from negative to positive. Okay, if we had negative slope, if we had a negative out the front here, we would expect the opposite. It's going from positive to negative. Okay, so we can make that argument with lines, and we can do the same with quadratics, right? We know if it has a positive out the front, opens upwards. If it has a negative out the front, opens downwards. That's quadratics, right? So you can anticipate its shape. So the important part here, look, you can, when you're doing the maths, okay, you can go from here to here to here, all right? So we can do it manually, we can do it using the intuitive process, and the other thing you can do is just use your graph, all right? You've established that the derivative is 2x take 4, you can graph it, and you can see from the derivative, it's below, we have negative values, and then it's above after 2. You can establish that from the graph. Now, you can even graph the derivative without knowing what the derivative is. Now, I don't think I showed you this last unit, so I'm going to show you it now. So pull your calculators out, and we're going to graph this function I've got here, x squared take 4x, take 2. So we'll just graph it over a standard V window. Okay, so what I showed you last unit was, look, I'm tracing along it and I've got the x and y values, but I showed you, and you should have it turned on already. I'll go back in there, sorry. Shift menu. I showed you there's this option called derivative, and we want that turned on. Most of you have it turned on already, and it should stay on once you've turned it on. And now when we trace along it, look, it's giving me the dy on dx value. It's telling me the slope for any point there. I'm going to say, what about when x is 2? Take me to that point. It's got the slope is 0. What about when x is 3? The slope is 2. What about when x is 4? All right, so that's what we learned last unit. Okay, we've got dy and dx, and it pops up there. It tells you the slope along the function. All right, so here's what we're going to learn today. Yep, is it if it's an individual issue, I might come see you a bit later, but unless there's any group questions. Okay, let's exit out. Okay, so we're still in the graph mode here. What we're going to do now is we're going to press Option, where Y2 is, hover over Y2. Okay, we're going to press Option, Calc, d on dx. Okay, d on dx. And what we're going to type in there is just y1. All right, so y corresponds with f1. See that? F1 and y. I'm going to press y, and then I'm going to press the number 1, because I want my calculator, close the bracket, I want my calculator. What is the function y1? y1 is x squared take 4x take 2. I want it to graph the derivative of y1. So even if I've differentiated it wrong in my process here, you can still get the right graph by getting your calculator to do it for you. So what was that? It was Option, Calc, d on dx. And you can see there's an option for the second derivative as well, right? Option calc d on dx. And we're typing in y and then the number 1. Now, before I graph it, all right, if I graph it right now, it's going to pop up with 2 functions. It's going to be a bit confusing. One thing we can do is we can go up and we can unselect this function. So I've scrolled up to y1 and I'm going to press the select button. Notice how it's no longer highlighted. The equals is not highlighted anymore. So that means it's not going to graph that function for me. All right, I can go back up and select it, and now it's highlighted it. It's going to graph all of the functions that have the highlighted equals. All right, I only wanted to graph one. I only wanted to graph the derivative function. There we go, there's the derivative function. All right, that's the equation of this line, right? 2x take 4. Y-intercept is -4, slope of 2. Okay, so that's how we can use our calculator to support us, right? Because I've got the old version of the calculator, I'm going to be using Desmos because it looks prettier and I can navigate that a bit easier. But I'll get you guys to follow along with the next question with our calculator. So, question 2, I've changed it because I was nutting it out this morning and it doesn't come out very nicely. So we're going to do this function instead. So can you change f of x to be x squared on top of x plus 2? Alright, so we just get rid of those minus 5x and the minus 36. So what's our process? Differentiate it, draw the sign diagram of the derivative, make the statements. Alright, so if we're going to differentiate this, we're going to need to use the quotient rule because we have one function divided by another. So we've got u is going to be x squared, u dash will be 2x, v will be x plus 2, and v dash will be 1. Let's smash all that together. U dash v, take away u v dash, all on top of v squared. Alright, we're going to process this and simplify it a bit. Right there you do have the derivative, but if we want to draw a sign diagram, if we wanted to do it manually, we're going to need to have it in a form that's easy for us to access. So I'm going to distribute this first. We've got 2x squared plus 4x, take x squared. And that's x squared plus 4x. Okay, so this is a rational function because it's expressed as a ratio. We have something at the top and we have something at the bottom. Now, this is something that keeps popping up here. If we have a rational function, if f of x is a on b, then f of x equals 0 when a is 0, and f of x is undefined when b is 0. Alright, so this function, the derivative function here, it's going to equal 0 when the numerator is 0. And it's going to be undefined. We're going to have an asymptote when the denominator is 0. So maybe you can see it from looking at it. If not, let's make the argument. X squared plus 4x is 0. We're going to factorize x and then apply the null factor law. Alright, so we've got the two roots. I'm going to draw a sign diagram here. We've got the two roots are minus 4 and 0. They're the roots. Alright, the roots occur when the numerator is 0. And then we have an asymptote when the denominator is 0. So we're looking at the denominator. What's going to make the denominator equal to 0? X is minus 2. Where's minus 2? The scale is not important. Getting the numbers in the right order is. Minus 2 is between minus 4 and 0. We indicate an asymptote with a dotted line, right? There's an asymptote at minus 2. So I've said the scale, the distance between these things is not important, but getting them in the right order is. For instance, if you put the asymptote over here and said minus 2, that's all wrong, okay? Just make sure you've got the numbers in ascending order, right? Okay, so we've got all of the important points for our sign diagram. Now we need to determine when's it positive, when's it negative. Now I don't have any quick, fast tricks for a function like this. So instead, we're going to look at the derivative function. We're going to look at the graph of the derivative. So in your calculators, change y1. Don't even change y2. You've already got it set so that it's going to graph the derivative. You're just going to change y1 such that it's our function x squared on top of x plus 2. That's the function. And what I'm going to do, what you can do on Desmos, is graph f dash of x. And we can see, I'll give you guys a minute to do that. Get the derivative function. So we can see that to the left of -4, it is positive. It's above the x-axis. Put a big plus there. Between -4 and -2, there's that asymptote, that -2, right? We can see it's negative over that region. Between -2 and positive, well, between -2 and 0, it's still negative. And then after 0, it is positive. Now, all of that information, right, I determined the roots and asymptotes manually, but all of that information is observable from the graph of the derivative, right? You can see the roots, you can see -4 and 0 very clearly, where the graph crosses the x-axis. The asymptote's a little bit harder to tackle, but you can see if you keep zooming out, it's just going down and down and down forever. And you should know intuitively it doesn't exist at that point because we're trying to divide by 0. Okay, so we've got the sign diagram, we're ready to answer. What's the point of all this? It's to say, when is the function, the initial function, increasing and decreasing? Do not get confused. We're not making a comment about when this function, the derivative, is increasing and decreasing. We're using the derivative to tell us about the original function. We're using f dash of x and the sign diagram of it to make statements about f of x. So f of x is increasing, but x is less than or equal to -4 and greater than 0. And decreasing okay, so this is a good example. I'm actually pretty happy with this one because this allows us to demonstrate why we include the point. Why we include the point? We include the point because that is not an asymptote. Here we don't include -2 because there is an asymptote at that point. The function doesn't exist there. Okay? So make sure we're getting our definitions around the arrows pointing the right way and make sure we're including the right one. So here it's negative between -4 and up to -2, but not including that point. Alright? Same here, it's negative between -2 and 0, but not including the point -2. So that's when it's increasing and decreasing. Now, we did all of that process to make statements about the original function. Let's have a look at the original function. I need to zoom out a bit to demonstrate it for you clearly. But what you can see is you're increasing until you get to this point here. All right, so you get to that local max, and then it starts decreasing. That's at -4. You're increasing till you get to -4, and then you start decreasing at -2. It doesn't exist, but it keeps decreasing after -2 until you get to 0, where there's that local mid, and then it starts increasing again. Very good. Okay, let's move on to the next one, unless there's any questions about that. So we're performing the calculus, we're using our calculator to help us generate the sign diagram. All of this information can be answered by looking at the original graph, all right? The original graph, the sign diagram, they should all confirm one another. All right, last one, e to the x. F of x equals e to the x. All right, f dash of x is going to equal e to the x. All right, so if we're going to draw the sign diagram, we want to know, when does e to the x equal 0? Never. There are no solutions that make e to the x equal 0. All right? E to the x does not equal 0. Here's another way you can confirm it, right? Is if you were to solve this equation, you would take the natural log of both sides. So you'd go ln e to the x equals ln of 0. And here you're going to get x is ln of 0. ln of 0 does not exist. Okay, there's no such thing as the natural logarithm of 0. If you think of the logarithmic graphs that we did in exercise 1c, there's an asymptote at x is 0. They don't exist there. So e to the x never equals 0. All right, think of the graph of e to the x. It looks like this. There's an asymptote here. The graph of ln x is the inverse of it. It looks like this. Okay, never touches the y-axis. So that confirmation, e to the x never equals 0. So what does this mean about the sign diagram of this function? It doesn't have a root, which means it's either all positive or all negative. All right? And so you can think about it by putting any number in there. If I put x is 1 in there, all right, we've got e to the 1. What does that mean? Well, e is 2.72 to the, that's a positive number. All right? Even if you put, get used to a thing like this, even if you put e to the minus 1,000, okay? What does that mean? It means 1 on top of e to the power of 1,000, which is 1 on top of 2.72 to the power of 1,000. Okay, what does that mean? It means 1 on top of 2.72 times 2.72 times 2.72, 1,000 times. Like down the bottom here, you have an enormous number. You have 1 divided, it's almost 0, but the point is it's still positive. So, positive. Regardless of the x value you put in, it's always positive, which means the function e to the x is increasing xer, increasing for all real numbers, never decreasing. Okay? And you can see that from the graph. Like if we graph e to the x, all right, if you're walking along it, you're always walking uphill. Although it looks like it's flat here, there's very slight increases in it, okay? So keep going, and you can see always moving up, never decreasing, always increasing. X belongs to all real numbers. Very good. Okay, so let's work through exercise 3b.